Hello there, welcome to this video on solving and interpreting rational equations in context. We're going to go ahead and look at rational equations in the specific context of objects moving through water, and we're going to interpret equations and solve them graphically. Okay, so just for prior knowledge here, there's a situation. Ulysses drove to see his parents who live 350 miles away. If his average speed was 65 miles per hour, how long in hours and minutes did it take to drive? Well, it's important to know that time is equal to distance over rate. And if I take his distance, which is 350 miles away, and then we divide by the rate, we get 5.38 approximately in hours. Now, the problem did ask in hours and minutes, how long did that drive take? So what we have to do is we have to take that 0.38 hours and convert into minutes. Well, that conversion rate is 60 minutes per 1 hour, so we get 23 minutes. So to answer this question, the drive took about 5 hours and 23 minutes. So we are going to be working with a formula here, which is common in physics. It is known as dirt. That's what my physics teacher in high school taught me. If you can remember dirt, that's going to be a very, very good formula for you going forward if you take AP Physics next year. So dirt is distance equals rate times time. Now let's talk about what the D stands for. Distance. That's how far something travels. And you guys know it could be in miles, could be kilometers, could be feet, could be centimeters. Then we have rate. That's what the R stands for. So rate is how fast something is traveling. Sometimes too, they give it to you in the terms of speed. Okay, and it's generally a ratio. So 45 miles per hour, 17 kilometers per hour, 12 feet per second. So it's generally going to be a ratio including units of distance and also in time. Why is that? I wonder if you can think about that. Why is rate always a ratio? Think about it. Okay, and then time. How long something is traveling or how long something takes. Okay, so, and again, those units could be different. Could be hours, could be minutes, could be seconds. All right, so what we're going to do in this lesson specifically, we're going to use this idea, but we're going to solve for time. So if I want time to be by itself from my top equation up here, if I want time to be by itself, well, I have to undo multiplication, which is division. So I'm going to divide both sides by rate, and then we end up with the main formula that we're going to be using for this lesson. Okay, so time is the distance divided by rate, and that's kind of what we saw in our practice problem. So make sure you highlight that or write that down. Time is equal to distance divided by rate. Okay, so before we start and look at a problem 2, there's something else that we need to talk about, some kind of just a conceptual understanding. We're going to be working with objects in water, and generally when an object is in water in a river or a stream, the water is going to be flowing one direction. So I just wanted to define, what does it mean to be going upstream? Well, when you go upstream, you're working against the direction of the water. You're going, say, this way, and the object, the water, is pushing back this way. So what do you think is going to happen to your speed? Well, you're going to slow down, that's right, because the object's, the water speed, is working against you, opposite forces. So overall, your rate of which you are moving is going to be slowed down. Now, couple that against with working downstream. Downstream. When you're going downstream, you're going with the water. So what's going to happen? Well, you're going to be working faster. You're going to move quicker when you go downstream. So here's just some of the formulas that we're going to be working with. The rate of an object going upstream is going to be the object's speed minus the water speed. Okay, so when you go upstream, you go slower. You're going to subtract the current. Okay, when you go downstream, when you go downstream, you're going to be working faster. You're going to add the water speed to the object's speed, and that makes sense. For me, water wasn't always like, I don't know, I'm not a swimmer. I ran track in high school, and I like to think of this about going uphill. Here's a hill. Here's me. I'll be happy because I'm running. And I'm running uphill. So when I run uphill, am I going to go faster or am I going to go slower? I'm going to go slower because I have to go uphill. And what's working against me? Gravity. Okay, so I go slower. All right. Whereas if I'm at the top of the hill, assuming I don't fall down, whee, okay, I'm running downwards. What's going to happen to me when you run downhill? Well, you're going to go faster, right? Because you're working with gravity. Okay, so just some conceptual understanding there. Okay, so here is our first problem. I'm going to go ahead and read it with word problems. It's always good to go ahead and just read it multiple times. So this says, Abraham rows 9 miles downstream. Ooh, downstream. In his canoe, and then 3 miles upstream to find a hiking trail. The trip takes him 2.3 hours. Abram's average speed in still water is 5 miles per hour. Okay, with the equation 9 over 5 plus c plus 3 over 5 minus c is equal to 2.3 hours, or 2.3, modeling the situation. Okay, so some information that they gave us here in context, and what they also did is they gave us an equation. So I want to right now just kind of break down how that equation was constructed, and this will help us interpret the equation in context, which is kind of what our task here is. So they say that Abram rode 9 miles, no, downstream, Shoreberg down. So I'm going to put a 9 in that box there. And then what was his rate when he went downstream? Well, I do know that he's going 5 miles per hour when he's going downstream. And when he goes downstream, it's like running downhill. Okay, he's going to go faster. So I'm going to add C, the current. Okay, so C will represent current. And then how long did it take him to go downstream? Well, I don't know, but what they did tell us is the total amount of time, okay? But what we do know too is that time is equal to distance divided by rate. Time is distance over rate. So I can construct a time that it took for him to go downstream. So 9 over 5 plus c. Okay, that's his time that it took to go downstream. Now let's go ahead and look upstream, okay? Then he took 3 miles to go upstream, okay? 3 miles to go upstream. And his rate, again, was 5 miles in still water, but this time he's going upstream. It's like running uphill. He's going to go slower, so I'm going to subtract C. Okay, so then what is his time that it took him to canoe upstream? Well, time is equal to distance, 3 over rate, 5 minus C. Okay, so how did they go ahead and get this situation or the equation to model the situation? Well, what they're really doing here is they are taking the time that it took Abram to go downstream. I'm going to use subscript. I'm going to say down. So time it took him to go downstream plus the time it takes him to go upstream, and that's equal to his total time, right? And we know that 2.3, that's the total amount of time that it took him to canoe up, or to canoe the whole river. Okay, so here's kind of how the equation's set up. His time downstream, right? 9 over 5 plus c plus the time it took him to go upstream, 3 over 5 minus c, is equal to his total time, 2.3. Okay, so that's how that equation is kind of set up. So now they're going to ask us some interpreting questions, which some of these are pretty easy. Explain what the 9 represents in context. Well, we can say the 9 represents the distance Abram went, and in this case it's downstream. Okay. Part B, explain what the 3 represents in context. Okay, the 3, which is here. So the 3 represents the distance Abram went upstream. Okay, not too bad. Here they're going to get a little bit more tricky. They say explain what the 5 plus c represents in context. Okay, so we can say the 5 plus c, which is here, represents Abram's rate, also known as speed, going downstream, right? 5 miles per hour plus the current, it's going with them downstream. Okay, part D, similar question. Explain what the 5 minus c represents in context. Okay, so we can say the 5 minus c represents Abram's speed, or you could say rate going upstream. Straightforward, right? Very, very straightforward. Okay, and then E, lastly, says explain what the 2.3 represents in context. Okay, the 2.3. Well, that was the total amount of time in the trip, right? We highlighted that in our initial reading. So we can say the 2.3 represents the total time the trip took in hours. We could include the units. All right. Okay. All right, part F, same problem. It says using the strategy of solving by graphing, solve the rational equation and explain what it means in terms of context. Include units, round to the nearest tenth when applicable. Okay, so first of all, they say using the strategy of solving by graphing. Okay, so what we're going to go ahead and do is we are going to graph. So here's Desmos, and you can go ahead and do this also in Desmos. We're going to go ahead and graph that equation. Well, actually, there's 2 parts. So I have 9 divided by x, that was downstream, right? Plus, 5 plus x. 5 plus x plus 3, he went 3 miles upstream. 5 minus the current because he's going upstream. Oh, do you see how I use C and now it says add a slider? They don't recognize C as a variable, so you need to use X in Desmos. So I'm going to use X, not X squared, X. There we go. Okay, and so now it recognizes that equation. And we want to know when is this equation equal to 2.3? When is it equal to 2.3? And I'm going to put y equals 2.3. You could put y equals over here. So I'm essentially using 2 equations, and I want to know when is the left side equal to the right side. So what I'm going to do is I'm going to zoom in here, and it looks like I have 2 solutions. I have one here and one here. They're touching. So when they touch, that is a solution. Okay. So what I'm going to do, I just need the x values. Those represent c. So, and they wanted us to round to the nearest tenth. So it looks like 0.5 and 2.1. Okay, so that's our solution. So that's solving by graphing. Okay, so, and they also say sketch or place an image of the graph in this place. So what I'm going to do, you can go ahead and take a screenshot, or you can kind of sketch this like a rough sketch if you want, or you can copy and paste it. So I'll just copy and paste. I think on the next example, I'll go ahead and do a sketch. So I'm going to copy it, and I'm going to paste it right here. Oh, or maybe not. Oh, okay, there it is. Come on, resize and move. Okay, so there's our image, and we can say, the solution is 0.5 and 2.1, right? Those are our two solutions. And in context, and this represents the speed of the river's current, okay, or the river, right? That's how much the river is traveling. And that's why in this equation, right, they're represented as C. So that's solving by graphing. We went ahead, we rounded to the nearest tenth like the problem asked. We did, did we include units? Did we include units? Include units. No, we did not. So I'm gonna go ahead, I'm gonna erase this. I'm gonna say 2.1, and this is miles per hour. So miles per hour. I don't put my and there. Okay. All right. So that's the basics foundation of this. I'm going to run through another example, and this time it should go a lot quicker. Okay, so here is example 2. It says a riverboat travels an average of 14 kilometers per hour in Stillwater. Okay, so they gave us the rate in Stillwater. Then it says the riverboat travels 110 kilometers up the Ohio River and 110 kilometers down the same river in 17.5 hours. Then they say the situation is modeled by the equation 110 over 14 minus c plus 110 over 14 plus c is equal to 17.5. Okay, so I just want to fill in the table again to kind of conceptualize this. So the distance it took, well, the riverboat went 110 kilometers, okay, in both instances, upstream and downstream. We also know that the riverboat was traveling at a rate of 14 kilometers per hour in both directions. But when it goes upstream, it's going to be working against the current. So I subtract the current. And when it goes downstream, it's going to be working with the current, plus c. Okay, so the total time is going to be, again, distance over rate. So time for downstream is 110 over 14 plus c. And total time upstream is 110 over 14 minus c. Okay, so I want to include hours too. This is we're talking hours here. So 14 minus c. This is kilometers per hour. Kilometers per hour, and then time we're talking is in hours. Okay. So now we're going to go ahead and just explain what it represents in context. So part A. Explain what the 14 minus c represents in context. Okay, so we could say the 14 minus c represents the rate of the riverboat traveling, and that would be 14 minus c. It's taking away the current. Okay, that's going to go slower, so that's upstream, traveling upstream. Okay, part B, explain what the 14 plus c represents in context. Well, we can say the 14 plus c represents the rate of the riverboat traveling downstream. Okay, 14 represents the speed of the boat. The plus C is the river, right? Going downstream, we're going to add that rate. Explain what the 110 represents in context. Well, the 110 represents the distance the riverboat, travels upstream as well as downstream. All right, part D. Explain what the 110 over 14 minus C represents in context. Okay, so the 110 over 14 minus C, the minus C tells me that this is going to be an upstream situation. And then since it's a ratio, this looks like it's going to be time. So we can say the 110 over 14 minus C represents the time it took the riverboat to go upstream. Okay. Part E is similar. Explain what the 110 over 14 plus C represents in context. So we can say the 110 over 14 plus C represents the time, and I'm going to include units because I feel like it, in hours it took for the riverboat to travel downstream. All right. Okay, part F. Again, using the strategy of solving by graphing, solve the rational equation and explain what it means in terms of the context. Include the units round to the nearest tenth when applicable. Okay, so we're going to solve by graphing. So I'm going to go back to Desmos. And I'm going to take the left side of my equation, the 110 over 14 minus C plus 110 over 14 plus C, and I'm going to graph that. So I'm going to go here and get rid of these two equations. I'm going to say, okay, so 110 divided by 14, doesn't matter which one goes first, minus, and instead of C, remember you have to use X, plus 110 divided by 14 plus X. So be careful when you're doing these problems. Sometimes the distances are different, so you'll want to make sure that your distance is over the right rate. So you'll want to make sure that those line up. In this case, they're both over the same, so it doesn't matter which one goes first. Okay, then this is equal to, y is equal to, and the total time I believe was 17.5. Let me just double check. Yeah, 17.5 hours. Okay, so wow, I don't see it at all. So what I can do is I'm going to go ahead and zoom out. So I'll zoom out. And oh, looks like here's where my two graphs intersect. So that's going to be our solution. So okay, so I have these two solutions. Looks like here and here. Now, here's where we're going to go ahead and talk about kind of what solutions make sense in terms of context. Now, remember, X is representing the speed of the current. And if you think about speed conceptually, what's the lowest speed possible? It's the speed I'm traveling right now, which is 0. I mean, if you take out, me, orbiting a planet, right? The planet rotating, but I'm not moving at all, so 0. So the domain for speed is non-negative, 0 to infinity, I guess, if I was the Flash, right? So my point I'm making here is this answer here of negative 4.472, this solution doesn't make sense contextually because speed can't be negative. So we're only going to take the positive solution here. So 4.472, which if they want to round it to the nearest tenth, it would be 4.5. Okay. So I'm going to go ahead and I'll sketch this one. So I'll give you guys an example. So here's my y-axis, my x-axis. Okay, so x, y, and we're going up by 5s. 5, 10, 15, 20. Okay, and our graph, let me see. So our solution's 4.472. So I'll also go by 5s over here. 5, 10, 15, 20. You just want to make sure it's kind of consistent, your scales. And now I'm going to go ahead and kind of draw, and I'll just switch up my colors. So it looks like, here. Looks like I had a minimum here at 15.714, and then we're going up. So here's kind of what the graph looks like. And then I have another straight line here at 17.5. And that's just a flat line, right? Okay. So that's an arrow. It's a very ugly arrow. Okay. So there's kind of our graph. And again, I left out the negative portion of the graph. You could go ahead and draw what's over in the negative section if you want, but really it's kind of extraneous. There's that word, extraneous. So where is our solution? Well, our solution is right here, and that is at 4.5. Okay, so we can say the solution is 4.5, and again, our units, kilometers per hour, and this represents the river's current or speed. It's the speed of the river. Okay, all right. Okay, I do have a practice problem for you. Here is the practice problem. You're going to go ahead and, hopefully you didn't see that. You're going to pause the video, and we're going to ask you some questions each piece. Okay, we'll go through A, B, C, D, E, and then F. Okay, hopefully you pause the answer and you inputted your solutions. Here is the solution to this. Part A, the 37 represents the distance in miles down the river. 11 point C represents the speed of the fishing boat when traveling upstream. Part C, 7.1 represents the total time in hours the fishing boat is traveling on the river. Part D, the 23 over 11 minus C represents the time the boat travels upstream. In part E, the 37 over 11 plus C represents the boat traveling downstream, the time it took to go downstream. Okay, and then F, the solution is 6.4 miles per hour, and that's the river's rate. Okay, all right. Hope you enjoyed the video. Hope you learned something, and I will see you next time. Peace.